Hello everyone, I am Dr. Sirajul Faisi. I welcome you in my YouTube channel. Today in this video, I am going to talk about active methylene compounds. So I will discuss in this video. First I will discuss about introductions of active methylene compound, then characteristics of tautomerism, then ketoenol tautomerism in ethyl acetoacetate, then difference between tautomerism and resonance, then acidic nature of methylene groups, then evidence for a structure of ethyl acetoacetate, and then evidence for a structure of ethyl acetoacetate, then physical properties of ethyl acetoacetate, then chemical properties of ethyl acetoacetate, and then application of ethyl acetoacetate. So, active methylene compounds. Active methylene groups containing compounds known as active methylene compound. So, the hydrogen in methane practically do not exhibit acidic character. However, when two of the hydrogen are replaced by electron withdrawing group, the rest of hydrogen become acidic in nature. The electron withdrawing group present on both sides attract the electron towards themselves and thus weaken CH bond of methylene. Thus, hydrogen atom can dissociate to give a stable anion. This same phenomenon applies to ethyl acetoacetate. The two hydrogen atoms bonded to methylene groups become acidic and reactive due to two electron withdrawing functional group, that is acetyl and ester attached O-methylene carbon. Thus, methylene groups attached to two electron withdrawing functional group is termed as reactive methylene groups. So, active methylene also known as reactive methylene. Some examples of compound containing reactive methylene groups you can see here. This compound ethyl acetoacetate, ethyl acetoacetate or ethyl 3-oxobutanoate, this CH2 groups. Here you can see malonic ester diethyl malonate and cyanoacetic esters, this one, and then you can see these compounds, examples of electron withdrawal. So overall, all the compound contain CH2, 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 electron withdrawing group, electron withdrawing groups, electron withdrawing groups. So this is the active methylene groups, these electron withdrawing groups and electron withdrawing group esters. So acetyl, ester, cyano, NO2, nitro groups. Now characteristic of tautomerisms. When two structure isomers are mutually interconvertible and exist in dynamic equilibrium, they are called tautomers. Tautomers are discrete chemical entities capable of isolation under suitable conditions. Tautomers differ from each other in stability. The less stable form is called labile form. The relative proportions of two formed in a tautomeric mixture varies from compound to compound and also with temperature. Solvent. Tautomeric transformations are also catalyzed by acids and bases. Tautomers exist in dynamic equilibrium. Their separations can be achieved only by a special method. Ketoenol tautomerism in ethyl acetoacetate. Aldehyde ketones and other carbonyl compound exhibit this special type of tautomerism, and this type of tautomerism has been observed in ethyl acetoacetate. It involves migration of proton from alpha carbon to carbonyl oxygen by following the mechanisms. So you can see the keto form, you can see the enol form. So tautomers containing the tautomer containing carbonyl groups is designed as keto form, and the other are containing hydroxyl group OH attached to a doubly bonded carbon is referred to as enol form, and this kind of tautomerism is termed as ketoenol tautomerism. So you can see this is the CO keto and this is the enol form. So double bonds here keto. So difference between tautomerism and resonance. As a matter of fact, there is no point of similarity between tautomerism and resonance. The former is the phenomenon describing the dynamic equilibrium between the isomers, whereas the latter is a concept for the representing a structure of molecule. And some of the important differences have been pointed out. You can see here. Tautomerism involves tautomers, which have real existence, whereas the resonance involves contribution structures, which are the hypothetical and do not exist. Tautomerisms involve the migrations of atoms, whereas of resonance to occur, all the atoms must occupy the same positions in all the contributing structure. Contributing structure differ from each other in the placement of electrons only. The tautomers are in dynamic equilibrium. Since the contributing structure is resonance are hypothetical, hence no such equilibrium is possible. The resonance involves shortening of single bond lengths and lengthening of double bonds length, but this is not so in tautomerism. The resonance lowers the energy of real molecules or stabilizes it, but this does not happen in tautomers. The molecule should be planar for resonance to occur, while it is not necessary in tautomerism. All the molecules of compound exhibiting resonance have the same structure regardless of the fact whether that can be represented or not, whereas the compounds exhibiting tautomerism have two or more types of molecule present as equilibrium issues. So the tautomerism is shown by placing reversible arrows, sign of equilibrium, between the tautomers, whereas resonance is depicted by placing double-headed arrow between contributing structures. Now, acidic nature of methylene compound. You know, methylene groups in ethyl acetoacetate is flanked by two electron withdrawing groups, N-acetyl groups and an ester group. The hydrogens of these methylene groups are ionizable due to electron withdrawing effect of the surrounding groups. Also, the negative ion obtained after losing the proton gets stabilized due to resonance. You can see here active methylene compound. Now you can see the active methylene compound situations. So what happened here? Removing this proton, carbon ion, this is resonance stabilized. Now my friends, ethyl acetoacetate offer a classical and most thoroughly investigated examples of keto-enol tautomerism. You can see here, this is the keto form and this is the enol form, and this is the inequilibrium sign. So this compound was first prepared by Gauthar, who designed it and it the enol structure, while Frankland and Lupa showed that ethyl acetate had keto structure. The presence of each of keto and enol form in ethyl acetate was supported by two sets of reactions. The reaction supporting keto form, evidence in favor of Frankland and Dupa formula. You can see this addition reactions, cyanohydride, disulfide. So this is supporting the keto form. You can see the mechanisms. It reacts with the hydroxylamine and phenylhydrazine to form oximes and phenylhydrazine respectively. Formation of oxime and hydrazone is characteristic of compound containing ketone groups. This reaction indicates presence of keto group in ethyl acetoacetate. You can see here phenylhydrazines. Ethyl acetate is hydrolyzed to acetone when treated with dilute acid or alkali, which indicate the presence of C ester groups. You can see it forms mono and dialkyl derivative, indicating the presence of active methylene groups, monoalkyl derivatives. All above reaction indicate the ethyl acetate exists in ketone. Now, reaction supporting enol form, evidence in favor of Gauthar's formula. With metallic sodium, ethyl acetoacetate forms the sodium derivative along with the evolution of hydrogen gas, which indicates the presence of hydroxyl group in ethyl acetoacetate. You can see. So, Second evidence, it produces reddish violet color with ferric chloride solution, and this point to the presence of carbon double bond carbon OH. Next, it discharges the color of the ethanolic Br2 solution, giving addition reaction which show presence of olefinic double bonds. You can see in these reactions. On treatment with phosphorus pentachloride, it forms ethyl ester of beta-chloroprotonic acid. PCl5 used for the conversion of hydroxyl groups into chlorofunctionality. Hence, it has been again proven from this reaction that hydroxyl group is present in ethyl acetoacetate. You can see in these reactions. Thus, the structure of ethyl acetoacetate remained a point of discussion until 1910. The controversy was resolved by North in 1911 when he succeeded in isolating both tautomers in pure form and showed that two forms are readily interconvertible. So North in 1911, who succeeded in isolating both forms, he cooled a solution of ethyl acetoacetate in light petrol to minus 78 degrees Celsius and obtained crystal which melted at minus 39 degrees Celsius, and this substance gave no coloration with minus 78 degrees Celsius and do not combine with bromine and was therefore the pure ketone form corresponding to Franklin-Dupas formula. North suspended the sodium derivative of ethyl acetoacetate in light petrol to minus 78 degrees Celsius and treated this suspension with just enough HCl to decompose the sodium salt. He now obtained a product which did not crystallize but set to glassy solid when cooled. This substance gave an intense coloration with minus 28 degrees Celsius and was therefore the pure hydroxy form corresponding to Goethe formula. The stability of enol form is ascribed to the formation of intramolecular hydrogen bond. You know, acid and bases catalyze the interconversion of tautomeric form, and the mechanism of 4-acid and base catalyzed transformation may be written as follows: keto form, and this is the enol form. You know this. Base, you can see anion and enol form. Now, proof for structure of ethyl acid by chelation condensation. Base catalyzes condensation of an ester containing an alpha hydrogen atom with the molecules of the same ester or different one to obtain beta ketoester is known as chelation condensation. So, two molecules alpha hydrogen of ethyl acetoacetate, it gives this ethyl acetoacetate products. So, what is the mechanisms? Generally accepted mechanism for the chelation condensation is shown here. You can see this enol, late anion, and then this compounds making this, and after keto-enol tautomerism will get this. So, following steps are involved in the above mechanisms. First, removal of alpha hydrogen by base, give resonance, stabilize anion. Formation of new bond between enolate, nucleophile and carbon of another molecules of ethyl acetate, and breaking of the bond to give stable molecules of ethyl acetoacetate. So, physical properties of ethyl acetoacetate. Ethyl acetoacetate is colorless liquid and fruity and has fruity color odors. Boiling point is 181 degrees Celsius. Is sparingly soluble in water but readily soluble in ethanol, ethers and most organic solid. Neutral to litmus, soluble in dilute sodium hydroxide, and it is enol form which dissolved to give sodium salt. Refractive index is 1.4 and gives reddish violet color with ferric chloride. Now, chemical properties of ethyl acetoacetate. Reaction due to keto form. Reductions. So, you can see starting from this compound, you have the ethyl acetoacetate, you have ethyl beta hydroxybutyrate with this ethyl acetoacetate. Now, if ethyl acetoacetate react with lithium aluminum hydroethanol, 1,3-butane diol is formed. So, this is the mechanism.